Okay. Good afternoon, all. In the previous lecture, yesterday, we've seen that the definition of vector space. Okay. What is the vector space? Let F plus dot be a field, then a non-empty set V together with binary operation, vector addition, and scalar multiplication. Okay. It's called the vector space over the field F if the all the 10 conditions holds, okay, or satisfied. Okay, what are the 10 conditions? First 5 conditions of abelian group. V plus is an abelian group. That is, V plus with respect to addition is abelian group. And the sixth one property, for any u belongs to V. Okay, which one? Look at here. This one. There is, V plus is an abelian group and there exists a unique vector 0. Okay, in V such that u plus 0 is equal to 0 plus u is equal to u for all u belongs to V. Okay, and all these are condition holds. If it is satisfied, then we can say that V over F is an vector space. Okay, so today we will see some more examples of vector space. Okay, now look at here, examples of vector space. Okay, example number 1. When F, that field is equal to set of real number. Okay, that is R. The field of real numbers. Okay, then if F is equal to R, then V over R is called real vector space. Real vector space. Okay, whatever be the V. Okay, then if the field is R, set of real number, then that vector space is called as real vector space. Similarly, if the V over C, okay, where C is the set of complex number, it's called complex vector space. Okay, so this is the first example. Now example number 2. Okay, the space is space singleton 0. Okay, the set containing only one element, that is 0. It's called 0 vector space. Okay, if the field F is equal to 0, that is the space 0 is called as 0 vector space, or we can say that null space, null vector space or null space. Okay, any doubt up to here? If F
No,
is
sir.
equal to singleton 0, then we can say that that vector space V over F is called null space, null vector space or null space. Okay, example number 3. R over R. Okay, V is equal to R and F is equal to R. V is equal to C and F is equal to R. That is C over R. And set of complex number over set of complex number are vector spaces. Are vector spaces with respect to two operations. Which one? Mutual addition. Mutual addition and usual multiplication. Okay, multiplication, usual addition and usual multiplication. It forms the vector space over the R over R, C over R, and C over C. But R over C, okay, R over C is not a vector space, not a vector space. Why? Because scalar multiplication to the vector. What is which condition fails here? R over C is not a vector space. We have one condition. V over F is the vector space if alpha belongs to F and U small u belongs to capital V. This implies alpha into U belongs to capital V. Okay, scalar multiplication law. If you multiply this scalar by to a vector U, then the product of these two elements belongs to the element of V. But here, if you take what is F here? F is equal to set of real number. And what is V? V is equal to set of complex number. Okay, set of complex number. So here, wait a minute. V is equal to, sorry, F is equal to set of complex number, and V is equal to what? Set of real number here. Okay. So if taking any complex number, suppose I is the complex number it belongs to, okay, 0 plus I is the complex number, it belongs to the set C, and 2 is the element belongs to capital R. This implies I into 2 belongs to कशामध्ये जायला पाहिजे मला? Belongs to set of V. That is it here. What is V? V is R. Okay. This is not belongs to R. Since 2 into I, that is 2I. This is the element not belongs to set of real number. Okay, so here the scalar multiplication law is fails. Hence, R over C is not a vector space. Any doubt? Okay, any doubt up to here?
No, sir.
Okay. Wait a minute. Now, example number 4. Example number 4. Let capital F be an arbitrary field. Be an arbitrary field. Okay. Then the set V, okay, capital V of all n tuples of the elements. Okay, set V is what? All n tuple of the elements of the field F forms a vector space. Vector space over the field capital F. Okay, where the vector addition and scalar multiplication are defined as, okay, what are the two operations? The two operations defined as follows. Okay, where the vector addition and scalar multiplication are defined as, look at here, What is the set V? First define the set V. Hmm. What is the nature of V? V is equal to V is what? The set, then the set V is of all n tuple of the element. That is the n tuple means what? A1, A2, up to so on an. This is the n tuple where all the elements are belongs to field F. Okay, for all ai belongs to capital F. So this is the nature of set V. Okay, now the scalar addition and vector addition and scalar multiplication are defined as, okay, the addition of two vectors, okay, elements of V, it's called as vectors. Okay, take any two elements from the set V, suppose a1, a2, up to so on an, and b1, b2, up to so on bn are the two elements belong to set V. Then addition of these two one set with two vectors a1, a2, up to so on an plus b1, b2, up to so on bn, which is equal to the addition of these two vectors defined as a1 plus b1, a2 plus b2, up to so on an plus bn. Okay, so addition of these two vectors defined like this. And if this a1, a2, up to so on an, this is the element from the set V, and alpha belongs to set F, that is the field F, then the scalar multiplication defined like alpha into a1, a2, up to so on an, which is equal to alpha into a1, alpha into a2, up to so on alpha into an. Okay, so this is the scalar multiplication on set V. Okay, if you define these two operation like this, usual scalar addition of two vector and scalar multiplication to the vector, then it forms a vector space. Okay, so this is the set V. So this implies this set V, okay, over the field F is a vector space. Any doubt? Any doubt up to here? Hello, am I audible?
Yes, sir.
Okay, is it my voice is clear?
Yes, sir.
Okay. Now this is the fourth example. Let F be an arbitrary field, then the set V of all n tuples of the element of F forms a vector space over F, where the vector addition is given by like this, and the scalar multiplication is defined like this. Okay, now the nature of set V is equal to curly bracket a1, a2, up to so on an for all ai belongs to, each ai belongs to F. Okay, so this forms V over F is a vector space. Now, example number 5. Let V be the set of all polynomials. Capital V be the set of all polynomials. Set of all polynomials a0 plus a1x plus a2x square. Okay, we know that this is the polynomial up to so on. Okay, an x raised to n up to so on. Okay, where we don't know the degree of the polynomial is finite or not. So here V be the set of polynomials, all polynomials. Okay, where each coefficient, the coefficient What are the coefficients of this polynomial? AI, all AIs, A0, A1, A2, up to so on, AN, up to and so on. All AIs belongs to field F. Okay, any arbitrary field F. Okay, so here the V over F is a vector space. Okay, what is the nature of V? Look at here. What is the nature of that set V? Set V is equal to A0 plus A1x plus A2x square plus up to so on an x raised to n up to so on. Okay, all the coefficient AI belongs to the field F. Okay, now what are the two operations defined on the V over F? The addition and multiplication. Okay, usual addition of two polynomials. Okay, usual addition of two polynomials and multiplication of two polynomials. Okay, so hmm, we define the vector addition and scalar multiplication. Scalar multiplication as the usual addition of two polynomials. Okay, and multiplication of two polynomials. Multiplication of a polynomial by a scalar. Okay, suppose f of x, this is the polynomial x square plus 1, and g of x, this is the polynomial 2, x square plus 2. Okay, 2x square plus 2. Then what is f of x plus g of x? Usual addition means what? This is x square plus 1, f of x. This one is g of x, 2x square plus 2. Taking the coefficient of x square together. Here the coefficient of x square is 1. 1 plus 2 is 3x square plus 1 plus 2 is 3. So this is the usual addition of two polynomials. Okay, and usual multiplication of two polynomials means f of x into g of x is equal to, for example, okay, x square plus 1 into 2x square plus 1, sorry, 2. Okay, now this is equal to x square into 2x square plus 2 plus 1 into 2x square plus 2. So this is equal to 2x raised to 4 plus 2x square plus 2x square plus 2, which is equal to 2x raised to 4 plus 4x square plus 2. Okay, so this is the usual multiplication of two polynomials. Okay, if you define the usual addition and usual multiplication on the set of V, that is the set of all polynomials defined on the field F. So here V over F is the vector space. Okay, that means V over F satisfies all the properties, okay, which seen in the previous lecture. Any doubt up to here?
Yes, sir.
Okay. कळते काय सांगतोय?
Yes, sir.
Yes, sir.
Okay. Okay.
Yes, sir.
Wait a minute. Now, example number 6. This set Rn. Okay. What is this set Rn? Anyone knows? N tuples, where all the entries belongs to R. Hmm. That student, what is the nature of Rn? माहित असेल तर सांगा, नाहीतर नाही म्हणून सांगा. In the circular bracket A1, A2, A3 up to so on AN, where all the AIs belongs to capital R. Okay, so this is the set Rn, n tuples, where all the entries belongs to R, is a vector space. Vector space over the set of real number. Okay, relate. What are the operations? Two operations: vector addition and scalar multiplication. The operations vector addition and scalar multiplication. Multiplication is defined by defined by. Hmm. If suppose take the any two element from the set Rn, suppose A1, A2 up to so on An, plus another element from the set Rn, B1, B2 up to so on Bn. So this is equal to A1 plus B1, A1 plus B1, A2 plus B2 up to so on An plus Bn. Okay, so this is the addition of two vectors in Rn. And what is the scalar multiplication? If k belongs to F, okay, and this is the element from this set of Rn. So k into this set of real number, na? K into A1, A2 up to so on An, which is equal to k into A1, k into A2 up to so on k into A. This forms a vector space. So here, if you define the two operations like this, the vector addition and the scalar multiplication, then Rn over R is a vector space. Any doubt up to here?
No, sir.
Okay. Now, this vector space is vector space. Which one? Rn over R. It's called which space? Euclidean space. Okay, Euclidean space. Okay, similarly, the vector space, if instead of R, if we take the set of complex number, the vector space Cn over the set of complex number, it's called unitary n space, or unitary space of unitary n space. Okay, n tuples are there, since they will take an unitary n space. Okay, and the nature of that Cn is equal to, set Cn is equal to A1, A2 up to so on An, where each AI belongs to set of complex number. Okay, any doubt up to here?
No, sir.
Okay, so these are the some examples of vector spaces. Okay, now we have one question. Prove that. Prove that capital V is equal to, okay, ordered tuple A and B. Okay, this is an ordered tuple such that A and B belongs to set of real number. Okay, it's a vector space. It's a vector space with respect to composition, that is the operation defined on this set over the set of real number, composition of addition and scalar multiplication. Scalar multiplication defined under. Okay, so he defined from the defined under the addition of two vectors defined like this, A and B plus C and D. If these are the two elements belongs to the set V, which is equal to A plus C and B plus D. Okay, and the scalar multiplication is K into A and B, which is equal to KA. This one is KB. Okay, where K belongs to set of real number. ओके, सो एव्हरी एलिमेंट त्या सेट मधलं प्रत्येक एलिमेंट कसं असेल तुमचा ऑर्डर ठेवतात. ओके, ए बी सी डी ई एफ काही असेल तो कसा असेल पण ऑर्डर्ड टपल मध्ये असेल. ओके, सो वी हॅव टू प्रूव्ह दॅट V, that is we have to prove that V over R, okay, that is set of ordered tuple V over R is a vector space. Okay, any doubt in the question? Any doubt in the question?
No, sir.
Okay, now solution. First we have to prove that first to prove that V plus is an abelian group. Is it correct? Okay, in abelian group there are 5 conditions are there. V plus, we have to prove that V plus is an abelian group. First condition of abelian group, closure property. Okay, take any two elements from the V. If the addition of that two elements belongs to that set V, then it satisfies the closure property. Okay, so let A and B and C and D are the two elements belongs to set of V. Okay, now A, sorry, the set AB order tuple plus the C and D, which is equal to कसा डिफाइन केला हा A plus C and B plus D. Okay, but what is A, B, C, D? A, B, C, D belongs to R, that is set of real number. But set of real number is what? Field. Field, it means it is a first group, abelian group. Hence A plus C and B plus D also belongs to what? A plus C high element kasat जाईल? This implies A plus B belongs to R and sorry, A plus C belongs to R and B plus D also belongs to R. So this implies this element belongs to what? Set of V. Okay, any doubt? Hence the closure property
No,
satisfied
sir.
by V. Now second one, associative property. What is the associative property? Take any three element first. Now instead of A, B, we take first A1, B1, A2, B2 and A3, B3. These are the three elements belongs to set of V. Okay. Now what is the closure property? A1, B1 plus A2, B2 okay, in the bracket, plus A3 B3, okay, which is equal to, now do the addition of these two one. So what we get here, A1 plus A2 and B1 plus, sorry, B1 plus B2, bracket complete, okay, plus, now the third element as it is. What is this? A1, A3, B3, okay, which is equal to, now do the addition of this one and this one. What we get here? A1 plus A2 plus A3 and B1 plus B2 plus B3. Okay, so this element we can write A1 B1 plus another bracket A2 B2 plus A3 B3. Okay, so hence there will be associative law holds. Okay, now the third one, identity property. Okay, what is identity property? A dot E or A plus E is equal to A na? This is the identity property. Now take any element from the set V. Suppose A1, B1. This is the element belongs to set of V. That is the ordered tuple. Okay. So there exists an element 0, 0 belongs to V. Okay, V 0 is the real number. So in the set V, we have 0, 0 element. Okay, so there exists an element 0, 0 belongs to V such that what we have A1, B1. Okay, what is the operation? Addition. Na? So here 0 plus 0, which is equal to what? A1 plus 0 is B1 plus 0 by the definition of vector addition. So here we get A1, B1. Okay, A1 plus 0 is A1, B1 plus 0 is B1. So this implies A1, B1 plus 0, 0 is equal to A1, B1. Okay, and this 0, 0 belongs to set of V. So this means identity law also holds. Okay, any doubt?
No, sir.
Now the fourth property, inverse property. What is the inverse property? Take any element from this set V. If A1, B1 belongs to set of V. So there exists minus A1 and minus B1. This is the element from the set of V such that what we have, such that A1 B1 plus minus A1 minus B1, which is equal to A1 plus minus A1, B1 plus minus B1. A1 minus A1 is 0, B1 minus B1 0. Okay, what is the inverse property? A plus minus A is equal to 0, then we can say that inverse property hold. Okay, so here the nature of element is A1 B1. Okay, so and this 0, 0 belongs to what? Set of V. So hence inverse property also holds, or inverse law holds. Okay, now the last one, commutative property. Take any two elements A1 B1 and A2 B2. These are the two elements belongs to set of V. Okay, now what we have, A1 B1 plus A2 B2 is equal to A1 plus A2 and B1 plus B2. Okay, what is A1, A2, B1, B2? These are the elements from the set R, set of real number. Set of real number is field. That means every field is an commutative group. Okay, so here the commutative law holds. So A1, A2, A1 plus A2, we can write this A2 plus A1. Okay, 3 अधिक 4 क्या किंवा 4 अधिक 3 क्या एकच येईल ना आन्सर. This is B2 plus B1. So this is equal to A2 B2 plus A1 B1. Hence, commutative law holds. Okay, any doubt?
No, sir.
Hence, set of all ordered tuples V with algebraic structure plus is an abelian group. Okay. Now, आता 5 condition prove झाले. Now 6th one. Take the K be the any element from the R. Okay, set of real number and A1 B1. This is the element from the set of V. Okay. Now the product of these two one. Then what we have K into A1 B1, which is equal to what? A into A1 by the definition of scalar multiplication and A into B2. This is the element from the set of V. Why? Because A1, B1 and the element K. These all the elements are the field of real number. But this is the field. Okay, this field means what? Addition and multiplication of R. So this is closed with respect to multiplication. So K into A1 and K into B1. These are the elements from the B, R. Okay, if these two elements belongs to R, then the ordered tuple K into A1 and K into B2. This is the belongs to V. Okay, so this is scalar multiplication law also holds. Okay, any doubt up to here?
No, sir.
Okay, now the next property is seventh property. What is the seventh property? Wait a minute. The multiplication by a scalar is distributive over addition. This one is the seventh property. The multiplication by scalar. Okay, multiplication by scalar is what? Distributive over vector addition. Okay, कशाने multiplication करायचं by scalar if alpha or k is the element from the set of real number and vector addition if a1 b1 and a2 b2, this is the element, these are the elements from the set of V, that is ordered tuple. Then what we have to show? K into these two elements. Okay, कसा असणार तो काल काय पाहिला पण k into u plus v is equal to what? ku plus kv असायला हवा. Okay, small v. इथे u कसा आहे तुमचा ordered tuple and v, the nature of u and v is here ordered tuple. Okay, so here k into first one, first vector is a1 b1 plus a2 b2. Okay, how multiplication by the scalar k is distributed over vector addition, the addition of these two vectors. Now which is equal to k into, by the definition of vector addition, this one is a1 plus a2 and this one is b1 plus b2. Okay. Now the definition of scalar multiplication to a vector. So this is k into a1 plus a2. Okay, comma k into b1 plus b2. Okay, so which is equal to a definition by scalar multiplication law. What we have? This is what? K
A
into
into A1 plus A into A2.
a1 b1 plus k into a2 b2. Okay, so here the multiplication by the scalar is distributive over the vector addition. Hence, we get k into these two vectors a1 b1 plus a2 b2 is equal to k into a1 b1 plus k into a2 b2. Okay, this is the seventh one. Now the eighth property, multiplication by a vector. Multiplication by a vector is distributive with respect to scalar addition. काल काय पाहिलं आपण, if u is the vector and these are the two scalars. Okay, what we have then? A into u plus b into u. Okay, or इकडनं multiply करा. A plus b, these are the two vectors, scalars. Multiplication by vector if this is u. So a into u plus b into u. Okay. Now here we have to prove that multiplication by a vector is distributive with respect to scalar addition. Now take any two scalar from the set of real number. Okay, suppose k instead of k, if you take alpha plus beta. Okay, these are the two scalar into vector. What is the vector? Suppose a1 and b1. This is the vector. Okay. Now the by the multiplication, where which is equal to where, right down here, where alpha and beta, these are the scalar, and a1 b1 belongs to set of ordered tuple v. Okay. What we have then? So this is alpha plus beta into a1. Okay. And alpha plus beta into b1. Okay, which is equal to alpha into a1 plus alpha into, sorry, beta into a1. Now this one is alpha b1 plus beta b1. Okay, so which is equal to, wait a minute, wait a minute. Wait a minute. Okay. What we have to do that alpha plus beta into a1, the alpha plus beta into b2. Wait a minute. What we have to show that alpha plus beta into u, which is equal to what? Alpha u plus beta u, na? Ah, this is the proof. Alpha plus beta, that is into u. What is u here? It is equal to alpha plus beta. Okay, direct his step. Okay, there is no need to write once again this step. Okay, so here alpha plus beta a1 and alpha plus beta b1 by the definition of, what is the reason? Definition of scalar multiplication. Scalar multiplication. Okay, so hence eighth property also satisfied. Now the ninth one. What is ninth one? In the third lecture, we seen that 1 into u is equal to u. Okay, here what is the identity element? 0 is the identity element, na? Okay, sorry, multiplication identity. Multiplication identity, multiplicative identity is 1 here. Okay, that is 1 into, what is u? A1 b1, which is equal to 1 into a1 and 1 into b1 by the definition of scalar multiplication, which is equal to 1 into a1 is a1, 1 into b1 is b1. So this implies 1 into a1 b1 is equal to a1 b1. Okay, that is 1 into u is equal to u. Okay, hence the ninth property also satisfied. Okay, any doubt up to here? Okay, good property. Okay, one more property is there. AB into U is equal to A into BU. Okay, now, and the last one, 10th property is AB. If A and B are the two scalars, instead of AB, if you take alpha and beta, if alpha into beta into what is A here? Vector A1, B1. Suppose this is the vector from the set V. So by the definition of scalar multiplication, this one is alpha beta A1 and this one is alpha beta B1. Okay, now taking common alpha, so we get beta A1 and beta B1. So this implies alpha beta A1 B1 is equal to alpha into beta, okay, into A1 B1. Okay, hence all the properties of vector space is satisfied. Hence, V over R is what? Vector space. Okay, any doubt up to here?
No, sir.
Okay, for today it is sufficient now. Okay, the remaining part, the subspaces. What is the subspace and the definition of subspace and some examples of subspace we see in the next lecture. Okay, for today it is sufficient. Okay, and thank you for the attending. You can leave now.
Thank you, sir.